All right, in this next video, we're going to continue talking about the directional derivative. Let me get back into the file here. If we scroll back up, whoa, why is it not going? There we go. We had talked about the graphical meaning. We had talked about the definition. And so now we want to talk about how to compute directional derivatives. So that's what this video is about. So the first thing we have to do here is we have to look at a key theorem. We're going to take a couple minutes and prove it actually. So this theorem says if you want the directional derivative, what you do, this is here, assuming you have a vector u cosine theta. I think I want a thinner pen here, cosine theta, sine theta. Then you just take the partial derivative of f in the x direction and multiply that by cosine theta, and then take the partial derivative in the y direction and multiply that by sine theta. And that will give you your directional derivative in the direction of the u vector. So what we're going to do here is we're going to take a minute and prove this. To prove it, we're going to fix a point. Got to slow it down here. Call it x naught, y naught. And then recall, we have our line in the plane is x naught plus t cosine theta, and then y is equal to y naught plus t sine theta. That was our 2D line in the plane, and that's in the direction of our u vector. So this is a line in the plane in the direction of u, which was cosine theta, sine theta. All right, so what we're going to try to do is we're going to try to prove then that the directional derivative, according to its definition here, that directional derivative is actually the partial derivative times cosine theta, the partial derivative with respect to x times cosine theta, and the partial derivative of y with respect to y times sine theta. So we're going to try to prove that. So the proof, not too bad. If we have x is on this line in the 2D plane is x naught plus t cosine theta and y is y naught plus t sine theta, then f of xy becomes f of x naught plus t cosine theta, and then y naught plus t sine theta. And you'll notice here that x naught, y naught is a given point. It's a fixed point. Theta is a fixed angle. And so what we have here, the only thing that's varying here is t. So this is some function g of t. So it's actually a single variable function. T is the only thing that varies there. Whoops, sorry about banging the table. So since it's just a function of t, we should be able to take its derivative with respect to t. So we want to find the derivative of g with respect to t. Of course, f is a function of x and y. So this would be the partial derivative of f with respect to x times the derivative of x with respect to t plus the partial derivative of f with respect to y times the derivative of y with respect to t. And so let's just call this that partial derivative notation. And the derivative of x with respect to t, well, if t is the only thing, if we're taking derivative with respect to t, then we have x naught is a constant, theta is a constant, so we just get cosine theta. And then similarly, we're just going to use that subscript notation. And then the derivative of y with respect to t will be sine theta. All right, now what we're going to try to show is that that is actually equal to the directional derivative. Right now we've shown that that's this derivative, this g prime of t. But that's not, we haven't proven that that's our directional derivative. So let's go back to the directional derivative. Go back up here to the definition. Oh, I I was missing something in my definition. This is kind of important. It's the limit as t goes to 0 of that. Let's do that in red. It's kind of important. We'll call it technical issues here, trying to record this video. But of course, if you don't take the limit as t goes to 0, it's the secant line. And we want to get the slope of the tangent line in that direction. And so we need to take the limit as t goes to 0. That's our directional derivative then. The limit as t goes to 0, f of, let's see. I guess we're just going to do it, yeah, f of, let's see, we want to find the directional derivative at, excuse me here, x naught, y naught. And so this will be the limit as, let's see, t goes to 0, f of x naught plus t cosine theta, y naught plus t sine theta, minus f at x naught, y naught, all over t. We're going to try to find, this was, the definition was the directional derivative at any xy. We want to find the directional derivative at a particular point. Okay, so what this is then, this is the limit as t goes to 0. If we look at this, the way that this is phrased, this f of x naught plus t cosine theta, y naught plus t sine theta, that's g of t. And then if there's no cosine theta, sine theta part, that means t is 0. So that's g of 0 all over t. And so if you look at that, you take the limit as t goes to 0, g of t minus g of 0 over t. That's actually the Calc 1 derivative for the derivative of g at 0. Well, then the directional derivative of f at x naught, y naught must then be this g prime of t evaluated at 0, but there is no t in the g prime of t, so therefore it is simply the partial derivative of f with respect to x times cosine theta plus the partial derivative with respect to y times sine theta. So to me when I read this, it seems a little convoluted, but that is the proof of this theorem. For your perspective, you're going to want to have a formula sheet down with this theorem written down, that you have the derivative with the directional derivative of a function is the partial derivative of f with respect to x times cosine theta, and then the plus the partial derivative of y with respect to y times sine theta. So let's go in and let's do a couple of examples on the next page. All right, first one here, we're going to try to find the slope of this particular surface in the direction of this particular vector. So let's go ahead and find what u is equal to. Cosine of pi over 6 would be square root of 3 over 2, and sine of pi over 6 is 1/2. All right, we have our particular point. This is our x naught, y naught. That's the negative 1, 3. And we're going to try to find the slope of the surface in this particular direction. So that means we want to find the directional derivative. In particular, it's the directional derivative in the direction of square root of 3 over 2, 1/2. So according to our theorem, that should be the partial derivative with respect to x times cosine theta, which is square root of 3 over 2, plus the partial derivative with respect to y times 1/2. And so if we take that partial derivative, the partial derivative with respect to x is 3x squared y squared times square root of 3 over 2. And the partial derivative with respect to y, 2x cubed y times 1/2. Now we want to evaluate this and look at the slope at that particular point, negative 1, 3. So the directional derivative at negative 1, 3 will be 3 times negative 1 squared times 3 squared times square root of 3 over 2 plus 2 times negative 1 cubed times, where'd it go, 3 times 1/2. And I guess we can lose the 1/2. What do we have here? 3 squared, 27 square root of 3 over 2 plus 3. So that's the directional derivative. And the directional derivative, remember, the directional derivative is a slope. It's a slope of the tangent line in that particular direction. You'll notice here that this is a pretty big number. So let me pop over to my maple graph here. So what I have here is in the middle here we have the directional derivative. You can see that. And then we have our point over here. Let's see, where is it? So we have our point. It is at, what was it, -1. X is -1, y is 3. But it's actually, if we need to look from above here. So you can see if we look right from above, there's -1, 3. Now the z value is actually fairly negative. But if we look at this from the side, you can see it's fairly steep in that direction. And you look at the green line, if I go directly from above, that's actually a perfectly straight line. It doesn't look straight from the side because those are the z values on that surface. So that's the curve on that surface in the direction of this blue unit vector. And the slope then, if we look from the side, the slope at that point is going to be very steep. The slope at that point, very steep in that direction. So that's that first example. Let's do another one here. Let's find the slope of the same surface at the point 2, 1 in a different direction. One issue here is that this v is not a unit vector, so we need a unit vector, which would be v over the magnitude of v. -1, 2 over square root of -1 squared plus 2 squared. So that would be -1 over square root of 5 and 2 over square root of 5. And now I have a unit vector. Let's see, partial derivative we already have. So the directional derivative in this particular direction at 2, 1 will be, let's see, what was that again? That was 3 times 2 squared times 1 squared times, oh, can I erase by pressing the button? Oh, look at that. I'm learning new things about my pen here. So 3 squared times 2 squared times 1 squared times -1 over square root of 5 plus 2 times x cubed times y times 1/2. And I guess we didn't need to write that. So what do we get here? 12 plus 8. 12 over square root of 5 plus, oh, no, not 1/2. Not 1/2. So 2, let's try this again. 2 times 2 cubed times 1, and then it's not 1/2 this time. It's 2 over the square root of 5, right? So let's see here. Let me see if that looks better. 2 cubed, 8. Oh yeah, I really have 2 to the 5th. 32 over square root of 5. Oh, this is not good. This is not what I got before. 2. Oh, that's why. This one is negative. There we go. Okay, that's better. Makes me nervous. I always want to do these ahead of time, and it makes me nervous when they are not the same as what I did the first time. So 20 over square root of 5, if we rationalize it, we could say 20 square root of 5 over 5, or 4 square root of 5. You don't have to rationalize, but if it makes it look nicer, this is definitely a better version. All right, I keep tapping the calendar, my finger. Let's finish up with this last question. Suppose our directional vector is, say, the unit vector in the x direction or the unit vector in the y direction. What would be the directional derivative? So I'm going to leave that leave this to be the end of the video and let you think about that. And that is it for this video.